Now let's look at a few examples where we will try to analyze the velocity and acceleration of various points on rigid bodies. So we'll start with our motion platform that we talked about before. You will find them in amusement parks. So let's say we have a parallelogram linkage system. This is your motion platform, and here are the seats, and there is a person sitting over here. Okay, and this person, let's say, is indicated by point P, and we want to know what is the velocity of this person P, or the particle. Okay, we're going to model that person as a particle. If, let's say, we know the angular velocity omega 0 of the input lane. So let's say this is point O2, this is A, this is point B, and this is point O4. So given to us is the angular velocity of O2A. Notice how I write it. I write omega, and then the subscript I write the rigid body, which is defined by the line O2A, and its angular velocity is given as omega 0 k hat. Why is it k hat? Because this is counterclockwise. So counterclockwise direction is treated to be positive, and that means it's k hat. Clockwise direction is considered to be negative. So this is not any different from what you have seen before. Okay, so that's negative k hat. So if this was already in the clockwise direction, we would add a minus sign in front of this quantity. Okay. We also know at this instant how O2A is located. Let's say this angle is given to you as theta, right? And this length is L. So because this is a parallelogram, this is also L, and this angle at this instant would also be theta, right? So what I'm going to do is I'm going to draw my coordinate system, because I'm going to be writing all these vectors. So I'll locate my coordinate system right at the point O2. Okay. So we are interested in the velocity of the point P. So find velocity of point P. Okay. So first of all, what is the motion of AB like? That's the first question we need to answer. Motion of AB, we have already seen, is a curvilinear translation, right? So it's a translation. What does translation really mean? Translation means that it's not changing its orientation. So if it's not changing its orientation, that means what is its angular velocity? Its angular velocity is 0. So omega AB is actually 0, because there is no change in orientation of this line AB, right? Now, its angular velocity is 0 at all instant in this case, right? Okay, so it's not that its angular velocity is 0 at one particular instant, it's 0 at all the time, right? Which also means that its angular acceleration will also be 0. Okay, so understand one thing. Sometimes the angular velocity could be 0, but angular acceleration may not be 0, primarily because the angular velocity is going to change at the next instant. In this case, the angular velocity doesn't change, it's always 0. So this is a function, and that means you can differentiate it and also say that angular acceleration is also going to be always 0. Okay, all right. So if angular acceleration is 0, right? If angular velocity is 0 and angular acceleration is 0, what can we say about, let's say, the velocity of this point P? Okay, so we can write velocity of point P by choosing a reference point on the AB. And remember, you always have to write this relationship for the velocity of the 2 points which belong to the same rigid body. It will be nonsensical to relate the velocity of point A with the velocity of O4, because there is no rigid body that connects A with O4. Okay, so that won't be possible. But you can relate velocity of A with velocity of B and with respect to velocity of P. Okay, so velocity of P we can write as velocity of A plus omega AB cross R of P with respect to A. That's our fundamental velocity relationship equation. Omega AB is 0, so this is 0, which means that this is equal to velocity of A. So velocity of P is equal to velocity of A. And if you write similar relationship between, let's say, P and B, what would you get? VB can be written as velocity of P, again, plus omega AB cross R of B with respect to P. This is 0, so that's equal to velocity of P. What this is saying is that every point on this motion platform has same velocity, right? They all have same velocity, and that is a property of a rigid body that is translating. Every point has the same velocity, and you will have the same relationship for the acceleration. So if you write the acceleration of P choosing A as a reference point, you have AP equal to AA plus omega AB cross omega AB cross R of P with respect to A plus alpha AB cross r of p with respect to a. Alpha is 0, omega is 0, so you get acceleration of p equal to acceleration of a will also be equal to acceleration of b. So for a rigid body that is translating, whether it's translating along a straight line or along a curved path, there its velocity of every point and acceleration of every point would be same. Okay, but that still doesn't answer the question, what is that velocity, right? What is that number? What is that vector that will give you the velocity of point P? But we just determined the velocity of point P is same as velocity of A. So if I can write the velocity of A, then our job will be done. Now if you look at the link O to A right over here, we can relate the velocity of A with the velocity of the point O2 on this rigid body. So let's do that. So velocity of A, choosing velocity of O2 as a reference point, and since O2 is a fixed point, I know its velocity is actually 0, is this plus omega of O2A, cross R of A with respect to O2. So omega of O2A, what is omega of O2A? Is given to you as omega 0 k hat. So let's substitute that. Omega 0 k hat. What is R of A with respect to O2? That is this position vector, which is equal to L cosine theta I hat plus sine theta j hat. So let's do the cross product, and we get omega 0 L cosine theta, k cross I is j hat, omega 0 L sine theta, and k cross j is minus I hat. So we get that. And that is the velocity of A, which is also velocity of point P, right? So from this, we can get the velocity of any point on this motion platform, because velocity of every point on this motion platform is same. What about acceleration? So let's write the acceleration equation. Acceleration of P is same as acceleration of A, and we will again choose O2 as a reference point, which has 0 acceleration, plus omega O2A cross omega O2A cross R of A with respect to O2 plus alpha O2A cross R of A with respect to O2. Now to get this, we have to know what alpha O2A is, right? We know what omega O2A is, but we don't know what alpha O2A is. So we'll simplify our problem and we'll say that this omega 0 is constant, okay? So if omega 0 is constant at all times, then alpha O2A is 0, right? So this will be 0. So we'll drop this term as a result of that. What we will have is omega O2A cross omega O2A cross R of A with respect to O2. So if we do the simplification, this actually is equal to minus omega square O2A times R of A with respect to O2. So this is minus omega square O2A, which is known to us. R of A with respect to O2 is L times cosine theta I hat plus sine theta j hat, and that's your answer for the acceleration of point P. Now let's look at an example where we have a rigid body doing pure rotation about a fixed point. So let's say we have a disc. It could be a cylinder, it could be a gear, doesn't matter, right? And it is allowed to rotate about its center of mass, and that point happens to be point O. And somebody tells you the velocity of a point A, which is r distance away from O, as this, okay? So velocity of A is given to you perpendicular to this line, that's direction, and somebody tells you this is, let's say, 5 meters per second, okay? Now the question is, what is the angular velocity of this disc or the gear, okay? So in this case, we don't know the angular velocity, but we do know the velocity of another point on this rigid body. Now when we write the velocity relationship, we write the velocity relationship between 2 points, right? So we have to know something about velocity with 2 points so that we can relate them. In this case, we know the velocity of A completely. We also know the velocity of the point O. Velocity of the point O is 0. So I can actually relate velocity of O with the velocity of A with the velocity of O, which is 0, plus omega OA cross R of A with respect to O. right? So since now we're writing position vector, I need some coordinate system, so I'll show that to you. And pretty soon I'm going to give you a very general method like I've been giving you for every module as to how to solve the problems. So we don't know what omega OA is, so we can assume that this is positive. So we'll just write this as omega OA k hat. Although in this case you can clearly see that omega is going to be clockwise, which means it should be negative. But remember, any vector quantity whose direction you do not know, you can always assume to be positive. If your guess is right, then answer will come out to be positive. If your guess is wrong, your answer will come out to be negative, right? So we don't have to worry about that. So we'll just write omega OA k hat over here, cross. What is R of A with respect to O? That's this vector. And that is R j hat. So we get omega OA times R, and k cross j is minus I hat. So this becomes minus I hat. And that's velocity of A. Okay. So velocity of A is given to you as 5 I hat, right? So we'll write that 5 I hat equal to minus omega OA R I hat. So omega OA is equal to minus 5 over R. Now you can see clearly over here that omega OA came out to be negative quantity, which means that it is actually going to be rotating in the clockwise direction. So if you know the value of R, you can find out what the angular velocity would be. Now let me say, somebody says to you that, here is another point, let's say, or maybe it's the same point A, but its velocity is actually this way. Okay, let's say this is V A prime. So it is the same disk, same gear, same cylinder, rotating about point O, and somebody says, here's the point A, and the velocity of this point A is V A prime, shown this way. That is not possible. How do you know it is not possible? Because if you look at the velocity relationship between A and O, it is VA is equal to velocity of O, which is 0, plus omega k hat cross R of A with respect to O, right? So this quantity is basically omega k cross R j hat, and that is minus omega R I hat, right? So even if you don't know what omega is, what R is, it doesn't matter what their actual numbers are, you can clearly see that this quantity is actually pointing along negative I hat direction if omega is assumed to be positive. If omega is assumed to be negative, then this quantity will be negative and this will be positive and this will be positive, right? So this is pointing along I hat direction. So velocity of A, even if you don't know any numbers, is always going to be this way. There is no way it can be pointing in this direction. That will be an impossibility. And you kind of know this because when we talked about kinematics of particles, you learned that if a particle is moving, okay, then its velocity is tangent to the path. So if you think of point A as a particle, the point A is actually moving in a circular path with O is at center, which means that if you draw the tangent at A, it is going to be pointing along positive I hat direction, right? So that's how you know that this will be an impossibility. A third example that we want to look at is the example of a wheel rolling without slip. Okay, so example, wheel or disc rolling without slip. And a wheel rolling without slip on a flat surface or an inclined surface or sandwiched between two surfaces is very common in engineering application. In fact, in this class, you'll find quite a few problems where you'll have wheels rolling without slip. So a wheel rolling without slip, let's examine that condition. So we have a wheel, and let's say this is rolling along a flat surface, and it's rolling without slip, okay? And ideally speaking, that's the kind of condition you want when you're driving your car or truck or your bike, right? You don't want wheels to escape. So what does that condition really tell you? So what that condition tells you is that if you look at the contact point, right? So if you zoom into this area, essentially, what you're looking at is the surface of the wheel, right? Let's say that point, a point on at the bottom of this wheel is P, and a corresponding point on the surface, okay, which we'll call Q. So at a particular instant, P and Q are coincident, right? They're right, on top of each other. They're not separate. I'm just drawing them separate over here because I want to show that you have 2 points, right? So there is a point P, which is on the wheel. There's a corresponding point Q coincident with P on the surface. So rolling without slip condition says that there is no relative motion between point P and point Q, okay? Which would be the case if this wheel was actually slipping, right? So if an object is allowed to slip, let's say I take the same wheel and I let it slip. So what does that mean? If I take this line OA over here, okay, then this line OA maintains its orientation as this moves. So when that happens, this is essentially doing a translation, right? It is not really rotating, and this line is maintaining its orientation, and this point is essentially slipping. This point is moving in this direction with some velocity, right? Whatever the velocity of this point is, center point is, let's say this is the center point. Let's say this is V0, this is V0, this is translating. So all the points on this disk are moving with the same velocity. Whether it's a point right over here, whether it's a point over here, all moving with the same velocity. But the corresponding point on the ground is not moving because the ground is stationary. So that means that there is relative motion between point P and Q. So during slipping, so this is slipping, velocity of P related to Q is actually not equal to 0. That quantity is some non-zero number. But rolling without slip condition says that velocity of P related to Q is 0. This is no slip condition. Now, what is velocity of P related to Q? Velocity of P related to Q is nothing but velocity of P minus velocity of Q. Okay? If the ground is stationary, then velocity of Q has to be 0, right? And if velocity of P related to Q is 0, which is the no slip condition, then we know that the velocity of P should also be 0. So at this particular instant, the point in contact with the ground is instantaneously not moving, which means that its velocity is actually 0. Now, that is not to say that the acceleration of that point P is also 0, because this particular point, which has 0 velocity, will go on and move to another location on the disk, and a new point will come in contact with the ground, but the original point P will have moved, which means that the acceleration of the point P is not necessarily going to be 0, even though the velocity of the point P at this particular instant is 0. Okay, so the no slip condition says that the contact point will have same velocity as the velocity of the surface on which it is rolling. In this case, the surface is stationary, so the point P has 0 velocity. Okay, all right. So let's say, we are given this much, but then that's not enough to analyze the velocity of every point on this disk. Let's say this is this geometry center O, okay, and we know that point O is moving with some velocity V0. All right, and the radius of this wheel is R. Now the question is, can you tell me what is the angular velocity of this disk? Okay, to get the angular velocity, we just have to relate it with the velocity of maybe 2 points on this disk. So this is the point P, whose velocity is known to us. We also know the velocity of point O. Maybe we can relate the velocity of the 2 points, right? So let's show our coordinate system, x and y. We can write velocity of O, choosing velocity of P as a reference point, plus omega k hat. Again, we'll just assume it to be positive, cross R of O with respect to P. This is 0, omega k hat. R of O, which is P, is this vector. That's radius times j hat. So we get minus omega r I hat, right? So velocity of O is equal to this. But velocity of O is given to you pointing to the right, so that's V0 I hat. And that means omega is equal to minus V0 over R. What that is telling you is that the angular velocity of this disk is actually in the clockwise direction. And that makes sense, right? The disk has to be rotating in the clockwise direction so that it can move towards right? So that tells you basically what the angular velocity magnitude is as well as the direction, if you know V0 and if you know the radius. On the other hand, you could be given omega and you were asked for the velocity of the center of mass, and you could find that as well, right? Okay, what about velocity of, let's say, a point Q, which is right above O? Okay, so it's diametrically opposite from point P. So can we get the velocity of Q? Sure, I can choose velocity of any other point on this disk and then relate them. So let's do that. I'm going to relate velocity of Q with velocity of point P. Why? Because I know velocity of point P to be 0. It's just a much more convenient point for me to choose. Plus omega k hat cross R of Q with respect to P. Omega we just determined is minus V0 R over R k hat cross R of Q with respect to P is this vector going from P, so that's 2R j hat. So we get r cancels, we get 2v0, k cross j is minus I hat, so that becomes plus I hat. So vq comes out to be 2v0 I hat. What does that mean? That is telling you that the velocity of this point q is actually twice of the velocity of the point O. Okay, so because this is doing a rolling motion without slipping, this is kind of expected, right? Because this is doing what we call a general planar motion, as we have seen before. And a general planar motion can be divided into a translation and a rotation. So if it was translating, then every point on this wheel would have the same velocity v0, right? So in that case, this point A would have the same velocity v0. If it was slipping, it was translating. But now it is rotating also, it is rolling, it's rotating as well. So rotation also contributes some velocity to the point A, and that in this case happens to be the same velocity as v0. So they get added together and you get actually twice of v0. Okay, so that's about the velocity. Now what about the acceleration? What can we say about acceleration of point P? We've already talked about this. We said that just because the velocity of the point P at any instant is 0 doesn't mean that the acceleration of the point P is also 0. But what we do know is that because along the tangential direction, this is the tangential direction, the velocity of P is same as the velocity of the Q, we also know, because of the no slip condition, the relative acceleration of point P with respect to Q along tangential direction would be 0. So no slip condition also says, that we know that velocity P related to Q is 0, but also acceleration of P related to Q in the tangent direction is 0. Now notice we didn't have to say that about the velocity, right? Because velocity is always along tangential direction. It's never along normal direction, but along tangential direction. And what is the tangential direction? Tangential direction is this line that is tangent to the point P. And in this case, this happens to be same as the direction of the surface, right? So acceleration of P related to Q in the tangent direction is 0. That's all we know. Okay, by the way, I just realized that I have abused the notation slightly over here. I'm calling this point to be Q over here, and I'm also calling this point to be Q here. So I shouldn't call this Q, actually. Maybe I should call it, I don't know, maybe we'll call it R, okay? So when I determine velocity of the Q here, this was actually R, and then this would be, of course, R, not, sorry, this is R, and this is P, okay? So this is R of R with respect to P, actually, okay? And this is now velocity of Q, which is, of course, 0. This is velocity of the point R, right? So there's a little mistake made over here in terms of the symbol, because I'm using Q for 2 points over here. So I want to reserve the Q for the point on the stationary surface, all right? So this is fine. This is okay. All right, so now let's try to relate the acceleration of point P with the acceleration of point O, which is the center of the wheel. So let's write that relationship. So acceleration of P is equal to acceleration of O minus omega square R of P with respect to O plus alpha cross R of P with respect to O. Okay, so first of all, how can we get the alpha? Well, we already know the alpha, which is given over here, so that's fine. Omega is also known. What do we know about acceleration of point O? Acceleration of point O is a0 I hat minus omega square R of P with respect to O plus alpha cross R of P with respect to O. Okay, so now let's begin to substitute everything in here. So we have a0 I hat minus omega square R of P with respect to O is this vector which is pointing along negative j, so that would be minus rj hat, and alpha is this quantity minus a0r, so let's write that minus a0 over r k hat cross minus r j hat. So we get a0 I hat plus omega square r j hat plus a0, this cancels, and k cross j is minus I hat, so we get that. So these two cancel and we get omega square r j hat. So acceleration of P is equal to omega square r j hat, right? So what this is saying is that the acceleration of the point P over here has a component only along this direction, right? There is no component of acceleration of P along tangential direction, and that matches with, what we were saying over here, which says that there is no tangential direction acceleration of point P, right? Because tangential direction acceleration would be same as the acceleration of the point Q, and the point Q is on the ground, which means that acceleration would be 0, right? If we found a component of I hat over here, then that would be a problem. Okay, so now we know how to compute the velocity and acceleration of a point on a wheel that is rolling without slip.